I'm Dave Smart, and I'm one of the engineers with John Deere that participates in the AEF project teams. The group that I'm participating with is Project Team 10. This is high-speed ISOBUS, and this is really our transition into the future of communications of connected systems, the implements and tractors. The high-speed ISOBUS is really a growth above and beyond what we experience today with ISOBUS based on CAN communications. CAN is originally developed from automotive technology, and for many years our successes have followed the same types of strategies that automotive has employed. So we've enjoyed the benefits of CAN. We've also, as automotive has seen the constraints of CAN. And so with multimedia in cars, with surround cameras, there's the demands for much faster communications. We're seeing the same analogy in the agricultural space with connected systems today. Control is quite functional, but can be limiting. So you can control, for instance, the application of chemical generally at kind of a section level, not down to a nozzle level. And for planting, the same sort of analogy there. There's typically section level control and data logging. And we'd like to move that to discrete row level control. So these are the challenges that today's ISOBUS doesn't scale very well into our future needs, and therefore the rationale for developing a high-speed ISOBUS standard. So we're some years away, I'd say, from an actual standard and products that you will find in the market space, taking advantage of the technologies that, again, automotive is doing a lot of the pioneering work that helps drive the cost down. The technologies they developed transition and scale well into our industry. And so we've got a lot of good direction from that and a lot of growth in that direction as well. Well, with CAN, from a bandwidth perspective, the ISOBUS standard is based on 250 kbits per second, or put it in terminology that might be a little more familiar, if we call it a quarter of a megabit. And with Ethernet technologies that many will be familiar with, that's commonly 10 megabit, 100 megabit, gigabit, and even beyond. So our focus is on 100 megabit and 1 gigabit communications. And this seems extraordinary compared to what we do with CAN. And quite frankly, in the next few years, we don't need that level of capability, but we're trying to create this new infrastructure to last for many years to come. So with that capability, we'll be able to, as I mentioned earlier, get down to the level of precision for row level information on planters or nozzle level information on sprayers. That's both control, data acquisition. That gives you a granularity in the field, GPS based quite commonly, for very precise control of applications, as well as for very precise measurements and yield information. I'd say really where this translates for a benefit is going to be in cost of input costs to the applications, as well as improved data analysis of the product of their work, so they can translate that into changes in inputs for the subsequent years. With this level of precision, we're not going to hopefully waste chemical. Certainly, we'll reduce the amount of overlap. We'll be more aware of the behavior of the planter, for instance, for skips and doubles, and just generally get much tighter control over the process. Just as in industry, waste in the process is waste of money, and we'd like to manage that as best we can and reduce that waste.